A major part in the cost of many chemicals that are used in industry and commercially comes from the associated costs of absorbing or stripping particular materials from streams of fluids. And this deals a lot with separation. Separation is a major theme in chemical engineering. In industry, chemical engineers are commonly faced with problems that involve having to separate streams based on components, and when separations get tricky is when the components you are trying to separate have similar physical properties, such as nearly identical melting or boiling points. And in cases like those, such as when you're dealing with the various stereoisomers, or like ethane versus ethene or propane versus propene separation, it can get very expensive because of the amount of work that is required to separate the species when they are so closely identical in physical properties. So when you have a stream coming in with various products, chemical engineers will use two systems referred to as absorbers and strippers. And they both perform separations. It's just a minor technical term. An absorber will remove a certain component from the vapor phase to a liquid phase, assuming we're working with a vapor and liquid phase. And a stripper will take A from the liquid phase to the vapor phase. Other than that, they're essentially identical. And what we would have is essentially a liquid stream of various components, with one of your components being a component of interest. Typically, we call that A, and it will flow through the various trays or stages of an absorber. So the absorber is the entire unit, and it's broken down into separate trays. And the number of trays you'll need is dependent on a number of variables that we'll get deeper into, as well as what kind of flow rate you need to run, and how long does it take to reach equilibrium in each stage and stuff like that. These are all important considerations to take into account when you are designing an absorber or stripper to use in practice. And so in the case of an absorber, we would have X is a variable we denote as the mole ratio of a component of interest in a liquid stream, and Y is the variable that denotes the mole ratio of the component of interest in the vapor stream. Capital L and capital V are variables typically used to define the molar flow rate of the liquid and vapor streams. And what we get overall is a nice set of variables to define an absorber or stripper that we can perform calculations on to get back of the envelope calculation for how big of a separation absorber are we going to need to reach some goals, such as achieving a 20% extraction or something like that in practice. And one of the key things to consider when designing an absorber or a stripper is the concentration of your component of interest. If the concentration is dilute enough, we can make assumptions and impose Henry's law, which makes calculations a lot easier later on because it simplifies the number of variables we have in our equations. But if the volume of, or the molar ratio of your component of interest is large enough to have a noticeable effect on the overall molar flow rates of your liquid or vapor, then we need to perform some additional calculations and convert it to a solute-free basis. Should have mentioned earlier that L and V denote the total molar flow rate, and when we go to a solute-free basis, we convert the variables to L prime and G prime. The primes denote that we are now only accounting for the molar flow rate of the solvent stream. So we neglect the mole flow rate of the component we are interested in separating and concentrate only on the moles of solvent present. And so why does this matter? So if we wanted to get an idea of an overall transfer ability of an absorber, we would use we would be able to, in dilute situations, be able to lump L and V terms together at each stage, which makes summing up the total ability of the absorber or stripper much easier to get an idea of what the overall performance would be. But if it turns out that you need to convert to a solute-free basis, we're going to have to work with some more variables. And two more variables you have to define would be this capital X and capital Y, which are denoted like this. And they represent the solute mole ratio to the solvent mole ratio. And once you have defined your variables, so step one is identify how concentrated is your component of interest. Maybe a rule of thumb would be plus or minus 10%. So if it's dilute enough, we can stick with the these types of regimes where we stick with L and V and neglect these other kinds of variables. If it's concentrated enough, then we'll have to go with a separate set of variables. The next step in your calculations, once you've defined and recognized which one of these two paths you want to go with, is to start defining equilibrium curves. And when we are dealing with dilute systems and we can use Henry's law, we can assume that the ratio of the component of interest in the vapor phase and the liquid phase at equilibrium will have a linear relationship, which we call K. And this is only for dilute streams. If it's not dilute, we have to define new variables and only we have to take into account the fact that the solute has an effect as it's being transferred throughout the absorber or stripper. And the reason we have to do this is because if we had a non-dilute system, equilibrium curves, once you get to higher concentrations, so higher liquid mole fractions or higher vapor mole fractions, they start to look more like exponentials or polynomial equations rather than linear equations. But as we can see, at low concentrations, we can approximate as Henry's law, which is nicer calculations, but it's often not the case when you start working with higher concentrations. And the next step, once you've defined your equilibrium curve, is to recognize what the lines actually represent in practice. So if we were looking at an absorber, for instance, and we were examining each tray or plate or stage, they're all synonymous, we would find that in a perfect world, the streams exiting, the vapor and liquid streams exiting a particular tray have reached equilibrium. So given sufficient time or a slow enough flow rate through the absorber, we can assume that the exiting streams at each tray have reached equilibrium. So we can say this stream here exiting, the vapor stream here exiting tray 1 is at equilibrium with the liquid stream here exiting stage 1 as well. And again, we're making an assumption that it actually reaches equilibrium, which is often not the case, and you'll have to take in yet more variables later on. But for an introduction to absorbers and strippers, this is a way to keep the concept and simplify variables to make the initial understanding simpler. And then your operating line is physically defined by the streams that are across from each other. So a liquid stream entering stage 1 and the vapor stream exiting stage 1 form 2 points. They form a point that defines an operating line. So physically, this is the intuition behind graphs you'll commonly see in chemical engineering books that show you these plots where they have equilibrium lines, and oftentimes on a test you'll be asked to plot an equilibrium line. And the way you do this is, first of all, 0, 0 has to be a point. When you have no concentration in your liquid phase, you can't have any concentration in your vapor phase. So that's always a nice point to go with. And then you can assume a linear relationship if it's dilute enough. And if you look at the composition, you have to be given the composition of a vapor stream exiting a particular stage and a liquid stream exiting that same stage, and that will give you a second point. And if you're in the Henry's law regime, you can just draw a straight line across your graph, and that's how you will define your equilibrium line. Now, the next step, defining your operating line, is dependent on whether or not you're working with separating A from a vapor to a liquid or separating A from a liquid to a vapor. If we are using an absorber, our operating line will lie above the equilibrium line. And the way we define our points is we look at the top of the column here on our operating line. So in this case, we have, you can think of x, y as just regular coordinates in an algebra class. Xn would be the inlet concentration of A going into your top plate. Y out is the desired or the given concentration of A exiting your top plate. That defines 1 point. And then another point, 2 points define a line, will be given by your bottom plate or any other plate if you know its concentrations, following the outlet flow molar concentration of your compound of interest, and the inlet vapor molar ratio for your component of interest. And so in that case, absorbers have operating lines that lie above your equilibrium lines, and if we are working with strippers, we now have an operating line that lies below our equilibrium line. And it's essentially the exact opposite for stripper. Your bottom point will be defined by the outlet mole ratio in the liquid and the inlet mole ratio of your component of interest in the vapor, and the opposite for the top point. And you can just draw a straight line like that. The slope of your equilibrium line is defined to be K, which is the Henry's constant for dilute systems. The slope of the operating lines for absorbers and strippers is defined to be the ratio of the total molar flow rate of the liquid over the total molar flow rate of the vapor stream. And it's common you'll be asked to plot this, and be able to understand the physical meaning of this stuff. So it is important to make sure to remember that if you're given 2 points, you can set up the generic equation for a line y equals mx plus b, set b equal to 0 for the equilibrium line because you know that has to be a point. And if you can find what your slope is, you've derived what your equilibrium constant k must be. And if you can derive what your slope is for your operating line for either an absorber or a stripper, you can now tell someone what the flow rate ratio is for your system. So that's it for this, and I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.